Let's go over Activity 8, where we focus on regularized logistic regression models and regularized trees with XGBoost. All right, so regularization is a pretty powerful tool that helps us build models better because we want a model that generalizes well. And if we get down to the math of it, it turns out that the generalization error model depends not only on its bias, basically how well it's fitting the training data, but then also on the variance of the procedure itself. And what that means is how much the form of that model changes if we were to switch up the particular set of individuals in the training data. The generalization error is kind of like the sum of the bias and the variance, and so when we do build a model, we need to pay attention to the variance component of that generalization error term instead of being completely focused on having the model minimize the bias, the error on the training sample. So regularization helps us do this directly, and we can get some practice employing this regularization technique with logistic regression. All right, so we're going to be working with the launch dataset in Reg class. So I'm going to load this up. And the launch dataset wants us to predict whether or not a new product that's being released is a success or a failure, depending on its value of profit after a few weeks. We have over 400 anonymized predictor variables. It's real data. It came from a Kaggle competition. They don't want to give away any trade secrets, so we're left in the dark as to what these predictors are. They're just referred to as X1, X2, etc. All right, so whenever we're going to do any sort of predictive analytics, we need to make sure that our data is in an okay form to actually use. So I have a few things that I want you to go through for data cleaning, and the first is to actually create a success column, something for us to predict. We're given the profit, and we're going to consider a product to be a success if that profit is bigger than a certain value. So I'm going to go ahead and create a column called success. It's going to be either yes or no, and we're going to use the if-else function to help us determine whether or not the values are successes or failures. So if launch profit is more than 4.5, like what we have here, we know that we're going to call that product a success. So the level is going to be yes, otherwise it's going to be no. Now, if I just run this, look at the output here, it's actually just text. Now, we can only predict the values of a categorical variable. Models don't predict text amount. So we actually need to convert this into a categorical variable with factor. All right, so we can check to make sure that we've done our job here by looking at the class. It's a factor, so we're going to be able to predict it. And now that we've made that success column, we're going to want to delete the profit column. We no longer need the monetary amount from that product. We're just predicting whether or not it's a success or a failure, so we can null out that column. Now, another big step in data cleaning, especially for regression models, is ensuring that our predictor variables are as symmetric as possible. Skewed distributions and outliers can really wreak havoc on logistic regression, and so there's a lot of variables to go and look through. I've done this for you and pointed out a few of these variables that really need to be replaced by their logarithms. All right, so what I'm going to do is to take these predictor variables, the first one was x4, and convert it to the logarithm of its value. Now I need to check to make sure I don't have any zeros here before I do this. Let me look at a summary of the first 13 columns of launch so that I can look to make sure that these variables that I should be converting are fine. So x4, the minimum is 2, x5, the minimum is 1, x7, the minimum is 1, x11, the minimum is 1, and x12, the minimum is 3. So I can just straight up take the logarithms. I don't need to add 1 or a constant to make sure that I'm not trying to take the log of 0. And once I've written the code, I'm just going to copy and paste. Do this slightly inefficiently. It'd be nicer to write a for loop to do this, but this isn't too bad. And we're just going to go and copy and paste over here so that we'll be taking the logs of all the original values. Having a symmetric distribution for the predictor variables makes our models a little bit more stable, a little bit less sensitive to particular individuals in the training data, and we like consistency. All right, so we've converted these into logarithms now. And then what we're going to do is to remove any columns that contain no information. If a column only has a single unique value, obviously that can't be predictive of an individual's class label, so we can just get rid of it. We have 419 predictor variables here. Maybe some of them have just all ones or all zeros. So I'm going to run this command, and what this command does is return a vector of trues and falses, or the unlist part does. The which part of it is going to basically tell me what column numbers have values that are just all the same number here. So if I were to look at, say, summary of launch x $15, all zeros. X $414, all zeros. So 2.delete, if I look at its values here, gives me a vector of column numbers that I can get rid of. So I can just redefine launch to be the original version, but without those columns. So we can get rid of those, and we see that we indeed have 349 predictors, so we're happy about that. All right, now there's still a lot of predictor variables. Algorithms run very, very slow if we have a lot of variables to work with. So we might be able to do some preliminary screening by determining what the important variables and maybe what some of the unimportant variables are. And one way we can do this is to run a random forest on the entirety of the data set, because the random forest gives us out variable importances, and we can just weed out some of the less important variables. All right, so let's go ahead and fit the random forest on the entirety of the data set. We're not using it for predictions, so it's okay to do this. We always got to set the random number seed before we run the random forest. We're predicting success from everything, and we're predicting it from launch. And let's do that with 500 trees, the default. And so we'll run these two lines as a pair. And then what we're going to do is look at a bar plot of the variable importances. So I can use the command bar plot. What do I want to be making a bar plot of? Well, if I take the output of summarized tree using random forest as the tree I'm looking at, the $ importance will go ahead and make this bar plot for me. So what do I see? If I have 348 predictor variables, they're sorted in order of importance, and I see that the importance drops off really quite precipitously. If I actually just make a vertical line at 100, because I'm going to suggest taking the top 100 predictors, it looks like, all right, I've captured, most of the really important stuff. There might be a little bit of information I'm just throwing away by ignoring those additional predictors, but I'm going to make my problem a lot simpler, and I like that. All right, so we run these two lines of code. Basically, good columns becomes the success column we want to be predicting, and then the names of those 100 most important predictors. So if I just run this command by itself, we see that, okay, these are the names, and so I'm going to keep those columns from launch, and everything else is going to get deleted. So now we have 100 predictors, and we're good to go. We can now get the data into a form that the ridge regression and lasso techniques can use. So we have to jump through a few hoops to do this. The author of the package doesn't do the heavy lifting for us. We leave that up to us. Step 1A, when we do regularized logistic regression, is to create a vector to store what the class labels are. And I'm going to always call this Y, just so that I can reuse my code without changing too many things. All right, so we're going to be taking out the success column and putting that into the Y variable, and then we're immediately going to null out that column, because the author of GLMNet, what we'll be using, wants a data frame of just predictor variables. So Y is a vector that has what the answers were, what the classes were. Launch now only is containing predictor variables, and that's what we have to do. Now, step 1B, we don't have to worry about here because we actually don't have any categorical variables. But in general, what we need to do is convert those categorical variables into indicator variables. In order to run this regularized logistic regression, every single predictor has to be numeric. Categorical variables aren't allowed. And so this command actually gives us a really quick and easy way to do this. So whatever the name of your data frame is, if you need to convert categorical variables to indicator variables, if we're using in a logistic regression model, we just change the name of these two quantities here. This line's already been written for us. We can just go ahead and run it. All right, so launch now contains only numbers. It's a data frame of only numbers here. Step number 2 is to scale the data frame. So what the regularized logistic regression does is it assigns a penalty to the complexity of the model, kind of trying to measure the variability or the variance of that model here. And it's going to measure that in terms of the size of the coefficients. Now the problem is coefficients depend on the units that the variables were measured in. But if we make every single variable have a mean of 0 and a standard deviation of 1 by scaling the data frame, then the size of the coefficient will mean something consistent from variable to variable, and that's exactly what we want. So what we're going to do is replace our launch data frame with the result of running scale launch. So now everything is going to have a mean of 0 and a standard deviation of 1. We can do a little bit of confirming that by getting the average for each column. And these are zeros according to R. Nothing's ever exactly equal to 0 in machine precision, but it's close enough that we're happy. And if we look at the standard deviations, indeed, they're all going to be equal to 1. All right, so now we're ready to actually start doing the model building. Step 3 is going to split our data into the training and holdout sample. So we're always going to set that random number seed because we split this training and holdout sample randomly here. And then we're going to write the train rows command. So we're going to sample 1 up to the n row of launch, picking row numbers at random. And in this case, I want 75% of the rows, so 0.75 times n row launch. So I have a random set of rows to put up. I always got to run those two as a pair. Random set of rows to put into training and holdout. So I'm going to make train and holdout by extracting those rows from launch. But remember, launch contains only predictors. So I actually need to split up my y vector, what was containing the answers, into training versions and holdout versions as well. So train.y being y bracket train rows will give us the answers for the training set, and we'll have the holdout answers here. All right, model building time. So let's try ridge regression. So what ridge regression is going to try to do is find a nice balance between the bias of the model and the variance of the model. So normally the way that logistic regression is fit is it chooses the coefficient so that the resulting model has the highest chance of reproducing the data that was collected, the training data. So it's basically only trying to minimize the bias, not paying any sort of attention to the generalizability of the model. Ridge regression is going to add in a complexity term to kind of balance this bias and variance. We're going to try to maximize the likelihood, but paying a bit of a price the larger we make those coefficients. And so that helps us to come up with a simpler model that hopefully will generalize pretty well. All right, so the question is, what needs to be the penalty term? It all depends on this value of lambda here, this shrinkage parameter, how much we're shrinking these coefficients towards 0 to make the model simpler. So we got to figure out what value is. We're going to do this with cross-validation, something that's built in, so we need to make sure to set the random number seed. And we're going to run this command just as is. So if every time you name your training data frame train, if every time you name your vector of answers on the training data, train.y, you can just use this command. Alpha is going to be equal to 0 for ridge regression, 1 for the lasso here, and n-fold is going to tell us that we're doing tenfold cross-validation to estimate the generalization error. So we'll run cv.glmnet, and we'll look at the results. So what we find is that if we make the penalty apply to the complexity of the model too big, the generalization actually gets worse. So why is this the case? Well, if we penalize the coefficient sizes too much, then those coefficients are going to be very, very close to 0, meaning each predictor variable is going to contribute just a little bit of information to predicting the class labels, and that might not be enough. Small coefficients might not be enough to have the model be a reasonable reflection of reality. And so the model is a little bit too simple. It's underfit, that's what we call that. So we actually do want a smaller value of the complexity term here. All the way out on the left, we actually see that it seems to be getting better and better. We could always, extend the values of lambda that we wanted to be looking at. But in this case, let's just take what the values of lambda suggested by this automatic tuning process. Here are two values that we might want to check out for lambda here, this penalty term. So the lambda that's associated with the smallest generalization error happened to be the one on the very far left. That's about 0.027. The one standard deviation rule says that, all right, well, two models whose estimated errors are within one standard deviation of each other are for all intents and purposes equivalent. So it says that if you want to get away with a simpler model, one that has a larger value of lambda, a larger penalty, well, you could get away perhaps with the lambda of 0.06. All right, so let's try these two out, and along with a penalty of 0, which would give us vanilla logistic regression. All right, so what we're going to do is define the values of lambda that we want to be looking at. We'll call that lambda grid. So we'll start out with 0, and then we'll look at this value of lambda, just copying and pasting that. I'm not going to type out the number itself because it's stored inside this object. There's my lambda grid. And then what we're going to do is run the glmnet command to do this ridge regression. I'm going to call this capital RR for ridge regression. And how does this command work? Well, I can never remember that, so I'm going to go to that file that I had posted that gives me a little bit of a cheat sheet for how these models are actually fit. And so I'm going to go down and I'm going to find where I fit ridge regression and copy and paste that here. All right, so I've named the training data train, don't got to change that. Train.y, don't have to change that. Alpha equals 0 for ridge regression. And here is where I specify the values of the shrinkage parameter I want to be looking at. So lambda equals what? Well, the values inside lambda grid. All right, so actually I can just wholesale reuse this command. That saves me a bit of time. We don't really need this threshold parameter here. We only need to do that if we get a warning saying that we didn't have enough time to estimate those coefficients. I'm going to leave that in here because it doesn't really do any harm. So we'll run it. Takes just a few seconds. And now we're going to make predictions. So I have some code for making the predictions for a shrinkage parameter of 0. Notice the difference in the syntax between the way we usually use predict. Still the name of the model we're using. S is going to tell us the value of the shrinkage parameter. Why it's S and not lambda, who knows? But in this case, I'm going to be making predictions for a shrinkage parameter of 0, basically vanilla logistic regression. Then I need to say on what data I'm making those predictions, and instead of new data equals, it has to be new x equals. That's just what the authors want. Type equals response to actually get those probabilities out, and then we can just get those predicted probabilities. All right, so now we want the area underneath the ROC curve, so we can make sure that the proc library is loaded up, and we can ask for that area. So what we have to do is we have to say what the answers were, and we've stored those as y or holdout.y. Those were the true class labels on the holdouts. Our predictions are stored in prediction 0. And so what we see is that we get a value of just at about 0.9. So vanilla logistic regression isn't a terrible model here. It looks like if we were presented with a random product that was a success, a random product that was a failure, our model has a 90% chance of assigning that successful product a higher probability of being successful. So it's ranking the probabilities pretty well. All right, well, what about these other models here? Well, we can pretty much just reuse our commands. There's only a few things we got to change. I'm going to change the name of this to be min here to represent that was the lambda associated with the smallest estimated generalization error. It's not an s equal to 0 here. Instead, it's an s equal to rr.cv $lambda min. Everything else is the same. Run it. Make sure that I'm using those probabilities. And there we go. So vanilla logistic regression gets an ROC curve area of 0.9. By regularizing the model, actually building into the model building procedure itself, kind of some awareness of what the variance of that model will be, it looks like that we significantly improve the performance by boosting up that area to 0.946. So pretty good, very kind of tedious to get the data into the form, but definitely a huge improvement over just standard vanilla logistic regression. All right, well, what about the lambda suggested by the 1SD rule? Well, let's see if that performs any better or any worse. We would imagine that both these models, since they were okay choices, should perform fairly similarly. So let's name this SE or 1SD, why not? And let's find the area under the ROC curve here. All right, so just a tiny bit higher. And I think what I want to do actually is I want to go and rerun these commands because I think the number that we actually put into Blackboard was a little bit different than what I have right here. So because this stuff is so sensitive to the random number seed, it's very easy to get slightly different answers every time you rerun the code unless you've set the seed in just the right places. It looks like in this case I am getting the right numbers though. So rounded up, this would be the number 0.946 that I would enter into Blackboard. We'd be getting credit for that. All right, so that's ridge regression, big improvement over vanilla logistic regression. What about the lasso? So the lasso measures the complexity of a model slightly differently. Instead of having the penalty be the sum of squared coefficients, it's the sum of the absolute values of the coefficients. So similar in spirit, but it has the advantage that the coefficients of irrelevant predictors can be set exactly equal to 0. Ridge regression only gets close to 0, never quite exactly equal to 0. So ridge regression will still always use information from every predictor, even if they're irrelevant. Maybe just a little tiny bit, but it's still going to be in there. All right, so the code to do the lasso is very similar to what we had actually just done. Actually, we need to figure out, okay, what's the values of the shrinkage parameter that we want. So we'll set that random number seed to 474, and then just run our command to help tune that value of lambda. All right, so what we see is that very little complexity or penalty here results in a model with a relatively high error. As we start penalizing the complexity more and more, it looks like the generalization error is expected to get smaller up to a point. If we penalize too much, those coefficients are too close to 0. They're not contributing enough information about the class labels to be useful. And so there's some sweet spot here. Looks like a shrinkage parameter somewhere between these two values might be the way to go. So let's just try them both out. Let's see how it works. So what we'll do is we'll go back up here and kind of copy the way that we had fit the ridge regression and just change what we need here. So in this case, we don't need 0 anymore. We've already looked at vanilla logistic regression. Instead, we want to look at the two lambdas stored from the results of running cv.glmnet. So we got those. Here's our lambda grid. And confirm that those have the values that I'm expecting. They do. So let's go ahead and fit the model. Now I'm going to call this lasso in all caps to denote that we're doing the lasso here. What do I need to change about this command? Only one thing. I'm going to change alpha equal to 1. That's what turns on the lasso feature. And let's go ahead and fit this. All right, so fit it really quickly. And now what we're going to do is make predictions on the holdouts and figure out that AUC. All right, so let's just borrow this stuff up over here. Just got to change a few of these things. Won't be too much of a problem. So our predictions are not coming from the RR model. It's coming from the lasso model. The shrinkage parameter we're using isn't referring back to the ridge regression. It's referring back to those values we found when tuning the lasso. So I'm just going to replace these values with the corresponding values for the lasso. Everything else is fine. 0.95 and 0.90. That seems awfully low. Let me try this again. Usually there's not that big of a difference between the lambdas with the, that's why. So notice I didn't change that from ridge regression to lasso here. All right, so let's make those predictions again. And we see that these two areas in the ROC curve are indeed very comparable to each other. Now, one thing that we do notice is that these numbers are also pretty similar to if we just done ridge regression. So making those numbers come out once again, we add 946, 0.948. We do slightly better with the lasso, 0.952 and 0.949 here, but it's not a huge improvement. But both are a huge improvement over the vanilla logistic regression. All right, so we want to make a comment here. We want to comment about which does better. The lasso does better, but only by a little bit. If we use the shrinkage parameters associated with the ones that gave the lowest estimated generalization error, lasso gives 0.952 and ridge regression gives 0.946. Bit of a bump in performance using the Lasso versus ridge regression, but not a huge amount. But compared to vanilla logistic regression, well, that made a huge difference. Looking back at the ROC area for logistic regression just by itself, 0.900, much, much lower. So both are much better than vanilla logistic regression, which had 0.901. All right, and as a bonus, the Lasso does typically perform a little bit better, but it also gives you additional insight over what predictors matter, because some of the coefficients may be set to 0 during the estimation process. That's never true for ridge regression. Nothing's going to be exactly equal to 0. Only the Lasso can do that. So how can we figure out which ones were set to 0? Well, if we look at coef on our Lasso, it's going to print out basically a list of all these coefficients. When you see dots, that means that those were zeros. So, all right, how many zeros are there? Well, why don't we look at the first column of that output. It's a lot of zeros. Let's figure out how many there are. So let's say length which, the coef equals to 0 here. We got 65, and then finally for the second column here, we have 59. All right, so you're going to enter in the larger of the two numbers on the blackboard, which is going to be 65. Now, you might wonder, okay, well, which one is which? So, unfortunately, I'm not exactly sure how the authors managed to do this, but I feel like they reversed the logical order here. So, one thing that we notice is that when we fit the Lasso, we pass the values of lambda as lambda grid here. And if we look at lambda grid, the lambda with the smallest penalty came first, and the lambda with the larger penalty came second here. But what you'll notice is that if we look at the number of coefficients that are 0 in the first column of the coefficient matrix here, we have a larger number of zeros than in the second column. And that doesn't make any sense. The larger the penalty that's going to be applied to the coefficients, the more those coefficients are going to be driven towards 0. So the model with the higher value of lambda should have more zeros. And so it looks like that the ordering is a bit reversed. So comma 1 is actually the second, or the very last element of your lambda grid vector. Comma 2 will be the second to last element of your lambda grid vector. They've reversed them. All right, so the larger is 65. So a lot of these coefficients are set to 0 with the Lasso. We could actually just eliminate those from the data frame because according to the Lasso, they contribute no information, and we would simplify our problem really quite a bit. All right, so to which shrinkage parameter does that number refer? So this comes from using the Lasso with the shrinkage suggested by the 1SD rule. Even though that was the second element of the lambda grid, it is the first column of coef Lasso. What a mix-up, we just got to make sure that we know this. So I'm going to put a big old note to remind us that this is the case. So it looks like the order that the models appear in the coef matrix is in the opposite, or is the opposite of their order in lambda grid. Inconvenient, but that's the way it is. All right, question number 9 deals with doing regularization with boosted trees using XGBoost. Now, this one is sufficiently complex enough and requires enough tuning that I've just straight up provided all of the code for you. So you can just copy and paste and run to see how the process works. Now, there's a strategy that goes behind here, what parameters are tuned first, then second, and it is an iterative process. It's very time consuming, but it typically does pay off by quite a bit. The most powerful models, the ones that are winning these Kaggle competitions, are these XGBoost models. I'm not going to go over it here because it does take a long time and all the code is provided, but please use this outline for tuning future XGBoost models. I'm not exactly sure if this particular model did any better than the regularized logistic regression, But a lot of that has to do with just doing a very, very simple tuning of this XGBoost model. Not necessarily picking out the optimal parameters, but just picking out a set of good ones so that the model performs okay.